Everyone, this is Mohammed Yaqub, and it's time of the week again for another STM32 tutorials. In today's tutorial, I'm going to show you how to use the HC-SR05 Ultrasonic Distance Measurement Sensor. So this is a very common sensor used in Arduinos, and today I want to show you how to use it on the STM board. And basically, the way this module works is that we have a trigger pin and an echo pin. These are the functional pins, and then a VCC and ground. The way this module works is that send a pulse. You need to send a 10 microsecond pulse on the trigger pin, and after that this will initiate the ultrasonic. And on the echo pin, a positive pulse would give you an indication of the time that the signal traveled back and forth to the object. So what we need to do to measure the distance basically is to send a 10 microsecond signal first on the trigger pin to start of the ultrasonic, and then measure the time of the positive pulse on the echo signal. And this will be equivalent to the entire trip time back and forth. So we need to divide this by 2, and this will give us the time the signal take. And we know that the speed of sound is 0.034 centimeter per microsecond. And we can multiply this by the speed of sound. This will give us the estimated distance in centimeter. And if you still think this doesn't make a lot of sense, you can take your time and watch this Arduino tutorial. I found this very helpful and explains exactly what the formula does. Alright, so I'll put a link to this video down in my description too, so that you can refer to it if you need more detailed explanation to the formula. Alright, so today I'm going to show you two methods on how to measure distance with the ultrasonic on the STM board. The first method is a very basic one, and it's easy for educational purposes and for students. It's just very straightforward. And the second method will be using STM internal timers, and that's for more of STM developers, people who want to integrate this to their operating system based application perhaps, and things like that. Alright, so I think that's enough introduction to the module. So let's just get started and set up a CubeMX project. On CubeMX, click on Access to Board Selector, and I'll be using the Nucleo F401RE board today. I quite like it, very convenient, has got a built-in serial debugger on UR2, so I'm going to use that, but it doesn't make any difference, you can use any board. So it's a Nucleo F401RE, this particular board. And on the pinout, I'd like to start by clearing all the pins and enabling the one I need myself. So clearing all the pins, and I want to enable PC13, and that's where the built-in push button is on, and I would like to give it a label and call it button. It will be very useful for me to use it later on the code if I gave it a label. And then on PA5 is my LED, so I want to enable this and set it to GPIO output. And I also would like to give it a label. I'm going to label it as LED. And then what I need to do is I need to enable my ultrasonic pins. And as I said earlier, the ultrasonic pins, the functional pins are the trigger and echo. Trigger is the output that we need to output from the STM to the ultrasonic module, and the echo is the input, so it comes out from the ultrasonic and goes to the STM. So I'm going to enable 2 pins for that. And if you look at the Nucleo pinout, you can see that there's a standard STM connector and the Arduino equivalent connector. And I just want to use PA8 and PA9. They're adjacent to each other, and I can take them out on D7 and D8 on the Arduino connector of the Nucleo. So I'll enable PA8 and set it to trigger, and PA9 is going to be my echo pin. So let's do that. That's PA8, right click on it and set the mode to GPIO output, and that's where I want to output my trigger signal on. And I'm also going to give it a label. I'm going to label it as trigger, and then PA9, set this as GPIO input, and I'd like to label it as echo. Alright, so that's my ultrasonic pins all set up, and don't forget that you need to connect the VCC to 5 volt. I don't think this module works on 3.3 volts, so it has to be connected to 5 volt and then ground to ground. And you can leave the output pin unconnected. right? One more thing here is that I want to enable my UR2 for debugging. That's on PA2 and PA3 because I want to send I want to print text to the terminal for debugging. So I'm going to print the distance and things like that. So go on connectivity UR2 and enable it in asynchronous mode, and this should be mapped out to PA2 and PA3 exactly. Because physically this is connected to the ST-Link on the Nucleo board, and just by plugging the USB to your computer, you will see a COM port and data will be printed out there. And if you have used the Nucleo long enough, you'll be quite familiar with this. Alright, so that's for my ultrasonic pins and the debugging pin. There's one more thing I'd like to do that I actually need to do, and that's to enable a timer for applying the microsecond delay, because I'd need to use some microsecond delay here, the 10 microsecond delay, and more delays to measure the signal here. So I'd like to use a timer for my microsecond delay, because the STM library doesn't have a built-in microsecond delay. And to do that, on timer peripheral tab, I want to use perhaps timer 4. You can use any timers on your STM, and all I need to do is to enable internal clock, and that's it. This will enable the timer. And then I need to set a prescaler. So let me check the clock configuration first. So on the clock configuration, by default on this module, if you enable it by CubeMX, you see that the maximum clock is applied, and on my timer clocks, both are 84 megahertz. So I'm sure that my timer 4 it runs at 84 megahertz. And what I want to do, I want to keep this delay run ticks at 1 microsecond. To do that, I need to set the prescaler to 84 minus 1, and this will scale the clock down from 84 megahertz to 1 megahertz. So every tick corresponds to 1 microsecond. All right, and then I'll leave the auto reload to, you can leave it as 0 and then set it in your code. So that's what I'll do. I'll leave it as 0 here by default. And then the counter mode is up. I don't want to enable auto reload. I'll leave everything else as in the default state. So that's all I need for my delay timer. So now we're ready to go to the project manager tab and store our project. First, select a location to store your project in. I want to store it at this location. It's a folder dedicated for the ultrasonic tutorial, and I want to call it ultrasonic tutorial. And my IDE is Keil Microvision 5. You can use any one you want, and I don't want to use the latest version, just version 1.24. Every version should run quite fine with this. Alright, so that's everything. We're ready to generate the code. So click on generate source code icon and wait for the code to be generated. And for any of my business contacts, you can always get in touch with me through mutexembedded.com. Alright, code finished generating. So click on open project. This will take you to your IDE. Okay, and on Keil, the first thing I want to start off with is that I want to compile the project, and then I need to open the main, and I'd like to write the microsecond delay function here. So the microsecond delay function has got the following prototype. It doesn't return anything. It's a void function, and I want to call it microsecond delay. And it takes a parameter of microsecond delay. It's an unsigned 32. I want to call it microsecond. That's the parameter that you need to pass. And then this will apply a microsecond delay. And for the definition of the function, I need to copy the function prototype down to begin number 4, where I can add my own user code. By the way, code finished compiling successfully initially without any errors, so we can carry on nicely. And the microsecond delay definition, as in this my preparation tutorial and my preparation code, it looks something like this. I'm just going to copy it over and explain to you the way it works. So that's the microsecond delay function. It uses a timer, and then it waits for this, and it sets the auto reload value based on the microsecond you want, and it assumes a prescaler that brings the clock down to 1 megahertz. All right. Let me just apply some final corrections so that I can use it to my new project. And instead of this being static to timer 4, I can just define my own define at the beginning. So I can define a micro TIM for my microsecond timer, and I want to set this to timer 4 because that's the timer I'm using at the moment. and then the function would be a generic microsecond TIM that I always need to define at the start of my project. So just copy this over to here, and this function will become generic to any timer that you enable. All you're going to do is to set the define at the beginning of each of your projects to micro STIM is equal to timer 4, and if you use another timer, just change the timer here at the beginning. Alright, so this will be a microsecond delay, a fairly accurate one. And then next, I need to apply the ultrasonic sequence and start using it. As the diagram explains, I first need to apply a 10 microsecond signal on the trigger pin. But at the very beginning, I want to set the trigger pin to low for a few microseconds, just so that I ensure the operation is stable. So that will be HAL GPIO right pin and my trigger pin. Since I gave it a label, all I need is to write a trigger, and Keil, when you click control space, will automatically give you suggestions, and it's my trig port, and then the second parameter is the pin number, and then I want to set this to low at the beginning, so HAL GPIO pin reset to bring the pin low for a few microseconds. So let's say microsecond delay, the function I just defined of, let's say, about 3 microseconds, and then start the actual ultrasonic measurement routine. And that will be, the first step is to output a 10 microsecond pulse on trigger pin, and that's what we'll do here. So I need to set it high, wait for 10 microsecond, and then bring it low. So delay would be 10 microsecond in this case, and then I can bring the trigger pin low. And then the second step is to measure the echo signal. So the echo signal, I need to wait for all of this time until this one starts rising. So there is some time delay between the 10 microsecond signal, the ultrasonic outputting the actual 40 kilohertz pulses, and then to the echo signal rising, and then we can measure the pulse width. So I'm just gonna wait for this one I'll wait for the rising edge and then start measuring the time. And for that, so that will be wait for echo pin rising edge, and that will be while my HAL GPIO read pin of the echo pin. So since I gave it a label, all I need to write this, and then this Keil will give me suggestion, and it's my echo pin at the second parameter. If this one is while this one is equal to GPIO pin reset, so while this one is low, I want to wait here in the infinite while, and as soon as we get a rising edge, this will break the while loop and jump into the next step. So step 3 is to start measuring echo pulse width in microsecond. And to do that, I want to define a variable that does the tick in microsecond. Just a moment. I'm going to define it in big number 1. I'm going to call it an unsigned 32 integer, and I'll call it number of ticks in some microsecond defined value. I'll initialize it to 0, and at the beginning here I want to reset it to 0 and then start my while loop. So what I'll do is I'll do a do while. I don't need to use a do while here. All I need is a while loop and while the pin is high. So while the echo pin is high, I want to keep counting a microsecond pulses. So while this one is equal to set, I want to increment this tick. And I designed this function, and I tested it on the oscilloscope. If you set a microsecond delay of 2 microsecond, the actual one on the scope would be 2.8 micro, and that's due to this function doing the initialization of the timer, which take few time, a few nanoseconds, and then that will be added and will result into 0.8 microsecond increment into the delay. So I know that a 2 microsecond delay here is equal to 2.8 microsecond actually, and then this number of ticks. So this will keep measuring 2.8 microsecond interval until we detect a falling edge. And that will be a very fairly accurate estimate of the time in microsecond of this pulse. And after that, once we counted the number of ticks in 2.8 microsecond increment, then we can measure the signal. So step 4 is to estimate distance in centimeter, so the distance in which the object is away from the ultrasonic. So for that, I need to define a few variables. The first variable is the speed of sound in centimeter per microsecond. And according to Google, speed of sound in centimeter per microsecond is 0.0343. But since we are traveling the distance back and forth, I need to divide this number by 2. So speed of sound in centimeter per microsecond as a constant float, call it speed of sound, and that's equal to this. But I also want to divide it by 2 because I'd have to divide by 2 anyway, because the distance, the time it takes, the time I measure here is actually the time the signal took to travel forth to the object and then back again to the echo pin, or rather to the ultrasonic measurement. So I can either divide the speed by 2, or I can divide the whole number by 2. So I'll just divide this by 2, and this will divide all the formula by 2. So it's easier, I'm just going to put it here. But the actual speed of sound is 0.0343. Okay, we'll hold that thought for a moment. I'm sure you'll understand why I'm doing this. So speed of sound, and then I need to measure the distance, which I'll define a variable for it too, and I'll call it distance. Alright, so my distance, I can measure it straight here. So distance would be equal to the number of ticks in here. I'm going to add 0.0f just so that this will be typecasted to float, and this needs to be multiplied by 2.8, which is the number of microsecond per tick. So this will give me the whole time the signal took, and then I need to multiply this by the speed of sound divided by 2. But since I put the divided by 2 in the speed of sound variable, I don't need to do any division here. Okay, so that's all. That's all. This will measure me the signal. Now, what I can do now is I can print it to the terminal so that I can see the measured signal and I can test the code. So step 5 is just print to UR terminal for debugging. Alternatively, you can go to the debugging mode and read this variable. So to print that to UR terminal, I need first to convert this to string. So I'm going to add a couple of more libraries here. So include string.h and standard IO.h. Alright, so that I can use the string functions. And I'll define a variable here for my string. So that will be a character array of, let's say, I'll call it UART buffer. A buffer of 100 elements so that I can print to the terminal. And then what I need to do is that I need to convert the distance into string. So that will go into my UART buffer, and I'll say distance in centimeter is equal to my distance variable in float, so 0.2f, or let's say 0.1f, and that will be a floating point with one decimal place, and that will be my distance variable. And I'm going to set a line feed encourage return, so that will go into a new line into my serial terminal. And now I can just transmit this over UART. And UART takes the UART handle, which is UART2 defined by CubeMX, and the second parameter is the buffer pointer typecasted into unsigned 8-bit integer, and that is my UART buffer. And the size I want to transmit is simply the string length of the UART buffer variable and a timeout of, let's say, 100 milliseconds. and then I'll just put a short delay of the loop. Let's say hold delay of 1. So I'm taking measurement every 1 second. So that's pretty much it. That's everything. Everything you need to do to measure distance with ultrasonic. So let me compile the code, load it to the board, and we're going to connect my STM board and test the everything. Okay, code compiled without errors. Now let's load it to the board, and we're going to open serial terminal to read our distance. I'm going to be using real term, so go on real term, and you see a port. The one and only is COM15, and I know my baud rate by default in CubeMX is 115200 of UR2, and you can find that when you go to pin configuration, to connectivity, UR2, you can see the baud rate is 115200. So that's the one. I click change, and now reset my STM board. And here we go. So it's saying that it's the maximum distance. Let me put my hand to hover over it. There you go. That's about 10 centimeter. I can see that roughly with my ruler. Then I put my hand up, distance increase, bring it lower, distance decrease. That's fairly accurate. I did measure it with a ruler. It's fairly accurate. It's not that bad. So that's how to use the ultrasonic with the normal mode. Now let me show you the other method in which you can measure distance with the ultrasonic using STM internal timers. And this will, what STM internal timer would do is that you would eliminate this indefinite waiting here for the pin for the echo pulse. For normal code, educational code, that's not a problem. But if using operating system application in which the code will be jumping between different threads, and you can't keep accurate timing anymore, that where STM internal timers are useful. So let me show you how to use internal timers to do the same thing with the ultrasonic. Okay, so to use STM timers to measure ultrasonic distance, I'm going to save this current project as another project, and we'll show you how it's done. So this is my project that I generated early. I'm going to save this project in a new file. So I'm going to call it STM Ultrasonic Tutorial Part 2, and I'll save it. So it will be saved as in a new folder. Now what I'll do is that I can disable my my echo pin, because I'm no more going to use the normal input, but I'll use the timer input capture input. So I can disable my echo pin, and what I need to do is that I need to enable a timer for measuring the pulse width this time. To do that, go on timers tab, and I'll use timer 3. That's an available timer. And you need to set the mode to, first of all, you need to select the clock source to internal clock, and I'll be using channel 1 in an input capture direct mode. That's the mode you want to use. That's an input capture mode to measure input signals. And what this mode does is that it keeps a counter running, and on the capture it will tell you what the counter value is. And we can make use of this fact to get the timer ticks at the rising edge and get the ticks on the falling edge, and then we can take the difference between the ticks in microsecond, and this will give us a very accurate estimate of the time of the positive pulse. Okay, and on the configuration I need to set a prescaler to make the tick in 1 microsecond. For that, I first need to check the clock speed. So on clock configuration, I know that my timer clocks APB1 and APB2 are at 84 megahertz, and to bring the tick down to 1 megahertz, which corresponds to 1 microsecond per tick, I need to set a prescaler of 84 minus 1. And the reason why I put a minus 1 is because 1 prescaler is equivalent to dividing by 2, and 0 is equivalent to dividing by 1. So that's why I need 84 minus 1 to divide actually by 84. And then for the counter period, I can set this as big as I can. So let's say 1 million. So 1 million microsecond is equal to 1 second. So that's just the counter. It will keep counting, but in my application, all I need is, as soon as I send the 10 microsecond signal, I can start my timer and detect a rising tick and a falling tick and take the difference between them. All right, and then let me just take this a bit higher. So the polarity of detection has to be both edges. I want it take a tick on both the falling and the rising edge. That's why I need to set polarity selection to both edges. And I can apply a filter, let's say, well, 5. That's just an input filter, low pass filter, to remove any possible noises. You can bring this value higher if you want to filter out some more. Well, let me bring it low to 4 maybe. Okay. One more thing is that I need to enable the interrupt of this timer, because at the rising and falling edge, this will generate an interrupt, which I can quickly jump in there and take the value. So that is everything I need to do for the second implementation using timers. So as you can see, this one, the timer 3 channel is mapped out to PA6. So that's where I need to connect my echo pin to. So the Nucleo pin out, I can see that PA6 is equivalent to Arduino connector D12. So that's where you need to connect your echo pin of the ultrasonic to the echo pin, and you have to keep the trigger pin the same, because we haven't changed that on CubeMX. Trigger pin is still on PA8. Alright, so that's everything. Let's go to project manager. Project given a name already with the same IDE setting, and we are ready to generate the source code. So click on generate source code icon. Okay, code generated successfully. Click on open project, and this will open Keil. Right, and as always, the first thing I'll do is I'll compile the project, and I'll start adding my code here. The majority of the code is the same, similar to the previous project. So I'll get back to the previous project. So the first few steps of sending the trigger pulse is the same. So I can just copy this over to my new project. So in the infinite while loop, this will set the trigger to low and send a 10 microsecond pulse. That's exactly the same. But the difference is in measuring the echo signal pulse. Well, and I also need the microsecond delay function, so I have to copy it over from the previous code. So that will be the function prototype and the function definition of the microsecond delay. So let me copy it over. It would have been much more convenient if I just generated over the same project, but I want to keep the main project so that I can link both source files down in the description of the video. So that's the function definition of the microsecond delay. I also need to prototype it at the beginning in private function prototype section, and I need to define the microsecond delay defined in here. So that will be define microsecond TIM is on TIM4. Okay, now all the errors should be gone. Exactly. Okay, so we added the microsecond delay, and we've added the 10 microsecond pulse on the trigger pin. And now the rest of the code, I want to copy it over to from my preparation tutorial just to save time. So the rest, what it does is that it starts the input capture timer, and then wait for an input capture flag to arrive, and then stop the timer, and then calculate the distance between the two edges. So let me copy it over, and I'll take you step by step on what the code does. All right. So now in measuring the echo signal pulse width, we need to start the input capture timer, and then let me also copy the variables over. So there are a few variables, and those are the input capture flag, capture index, and capture edges. So I'll copy them over. Well, don't worry, if you think I'm going quick, I'll get back and explain to them step by step, but I want to save time by copying the code over from my preparation code. And also the distance variable that I defined early in the video, that's the floating point, speed of sound, also in the UART buffer. I'll copy them over to the new project. All right, perfect. Good. Now, for the input capture, when I start the input capture timer, I need the input capture callback. So whenever this detects a rising edge, it will jump into the callback function in which we can read the ticks. So you'll find those down in my preparation code. I'll copy them to my code too, and that is the HAL TIM input capture callback. I'll copy it and I'll explain what it does. All right, and don't worry, I'm gonna put the main.c file down in the description of the video, so you can follow up and use the same code I'm using. Right, so this is the TIM input capture callback, And what I want to do here is that I'm just toggling my LED whenever a capture happens, so that I can see physically on my board that the green LED will toggle on every echo signal pulse. And then if the capture index is equal to 0, and that's the first edge, that means this is the first edge, then I want to read a capture and store it into edge 1 time. And then I will increment the index to 1. And the second time this interrupt happens, that is definitely my second edge. Right? Then I'll take another value and store it in edge number 2 and reset the index. And then set my input capture flag to 1 so that the main knows that we have finished capturing the time for the rising edge and the falling edge of the signal, so we can proceed and estimate distance. Alright, and the advantage of this code is that in here is gonna keep a do while with a time out of certain value. In this case is 500 millisecond, so it's not gonna wait indefinitely. If the pulse didn't arrive for any reason, something like maybe the wiring went loose, then it's not gonna hold your program into here. It will just time out and stop the input capture time and then try again when it comes back. This is very, very useful. This implementation is useful when you're using operating system in your application. All right, so once the flag arrives, then we know that we're taking capture of edge 2 and edge 1. Then I can reset the flag and stop the input capture timer, and now I can just do a quick check as well. If edge 2 time is bigger than edge 1, then I measure distance. Otherwise I'll set distance to 0, and then I can bring distance to my terminals, similar to what I did with my previous code, and set a time delay. And I also need to include the string.h so that I can use the string function. So I'll copy the includes over from my previous code too, and those are the string library and the standard IO. Alright, those go to the include section. And here we go. So the only difference is into capturing the echo pin. So now let's do a quick test and run this code and see how it works. Alright, well first, this one still multiplies by a static number. I want to use the speed of sound variable that I define. That's much more efficient code implementation wise. Alright, so that's everything. Let me compile the code, load it to the board, and we're going to have a look at the serial terminal and to test this code over again. Alright, loaded to the board successfully. Back to the terminal, let me open the board and reset my STM. Alright, it's not working. Let me see what the problem is. One moment. Alright, okay, the problem is that I haven't changed the pin over to PA6. My echo pin is still hooked up to PA8. So, as I explained, PA6 is on, that's where the timer input capture in. PA6 is equivalent to D12 Arduino connector on the Nucleo. So let me just change my pin over, and I expect the values to pop up here. So let's do that in real time. All right, let me reset this and reset my STM. Right, okay, there is one more reason why this has happened. That's because the period is set to 0 on timer 3. So I set it on CubeMX, but for some reason it didn't appear in here. I think it's because it exceeded the range. So when you go to timer 3, you see that the period is meant to be... All right, okay, so I forgot to set a period. Very clever of me. Okay, so back on here, so you need to set a period of, let's say, 1 million minus 1, so that equivalent to 1 million microsecond is equal to 1 second. This is just the maximum span this timer can go, but we're not going to use up this range because we're just taking a tick on the rising and falling edge. So compiling the code, loading it back again to the board, and back to the terminal, and reset the terminal and reset my STM. And here we go, we started measuring signals. When I put my hand over it, over 10 centimeter, here we go, it's fairly accurate, very, very accurate. I expect this one to be much more accurate than the previous implementation due to STM doing the time estimation or time measurement in hardware level. There we go. Then there you go, you can hover my hand over it, it's very fairly accurate measurement. Alright, so this brings me to the end of my tutorial. That's everything I want to show you today on the ultrasonic. I hope you enjoy it. Thanks for watching, and as always, if you found it helpful, don't forget to hit like and subscribe, and perhaps share it with a friend. And for any of my business contacts, you can always get in touch with me through mutexembedded.com. Thanks for watching, and I'll see you in the next video.